Morning, nerds. We're almost finished with the unit. Almost. Got unit 14 today and tomorrow, and then unit 15, and we are, well, I meant to say we're almost finished with topic 2. We have unit 14 today and tomorrow, unit 15 next week, and then technically we are 2/3 of the way through our curriculum. Exciting stuff. I know, right? Exciting. Topic 3 is all trig. Yes, but it'll be the rest of the year. No clue. I don't know. No clue. I have no idea how big it is. I just know it's the rest of the year. Okay, guys. This unit 14, is all about uses of logarithms. How they're used in real-world situations and how we use them to solve real-world exponential equations, things like that. So there's some vocabulary here showing you how logarithms are used and exponentials are used in everyday life. We've got the Richter scale. I'm not reading all of this. We've got the pH scale. I'm not reading all of this. And we've got Newton's law of cooling. Again, not reading all of this. You do not need to have these formulas memorized. Okay? And that's why I'm not going to bother reading it until I need it, because there's no way I'll remember it all anyway when I get to the questions that require this material. So yeah, we will use all of these within the notes, but you don't have to commit them to memory. Cool beans? Cool beans! Awesome. Great. A satellite is launched from a spacecraft and will reach a stable orbit 300 kilometers above Earth if it reaches a velocity of 7.7 kilometers per second. Suppose a rocket has a mass ratio, R, of 26, an exhaust velocity, C, of 2.85 kilometers per second, and a firing time, which would be T, of 120 seconds. We're going to use this formula to determine whether the satellite will reach a stable orbit. And remember, it's a stable orbit if it gets to this velocity. Basically, all we need to do is plug in all the numbers that were given. We were given time, we were given C, we were given R, and we're just going to grab handy-dandy calculator and plug them in. It's actually a very easy question. So the velocity will be negative 0.0098 times 120 plus the 2.85 natural log of 26. I don't know if this is a true formula or not, but who cares? Negative 0.0098 times 120 plus 2.85 natural log of 26. Let's see what we get. Boonk. Okay, 3 decimals. Actually, if you round it to 3 decimals, it'll bump up to 8.11. So, was that fast enough to reach a stable orbit? Yeah, it was bigger than 7.7. So, yay, stable orbit. Very simple question, right? I wouldn't even call that uses of logarithms or solving anything. That was literally just grab a calculator. Light work. Next. The amount of energy, capital E, in ergs, and by the way, this is a unit of energy. Yeah, ergs, yeah. They are, 1 erg is equal to 10 to the negative 7 joules of energy. So if you're a physics student, you know about joules. No. 1 erg is not that much. 10 to the negative 7 joules. So anyway, the amount of energy in ergs that an earthquake releases is related to its Richter scale magnitude, capital M, by this equation. So log of E, this is not log base E, this is log of the amount of energy in ergs. 11.8 plus 1.5 times the magnitude. On February 5th, 2023, an earthquake measuring 7.8 on the Richter scale struck southern and central Turkey. We want to know how much energy it released in ergs. It's going to be a lot. It's going to be a lot. Okay? Let's see what we get. What color? Orange feels like earthquakes. So log of capital E is 11.8. I don't have a brown pen. If I did, it'll look like purple or black. Plus 1.5 times this 7.8 Richter scale. How do we get E by itself? Yeah? Base 10, because this is log base 10. So what we need to do is use exponential base 10 on both sides. And that'll be 10 raised to all of this stuff. And that's going to isolate E in ergs. So E is 10 to the power of whatever this number is. And you know what? We might need to leave it in 10 to the power of format. Let's see. Because that number might be really big. Yeah, I think we better leave it in exponential format. Because if you try to raise 10 to that power, it's going to give you something in scientific notation. So we might as well just leave it in 10 to the power of 23.5 ergs. Bless you. Why do we what? Leave it like this? Well, if you don't leave it like this, then you'd have to write it as 3.162 times 10 to the 23 ergs. I mean, it's got 23 zeros after it. It's a boatload. 23 and a half zeros, yeah. Good question. Anyway, to be honest with you, though, like most people don't know much about ergs. I mean, I had to look them up to even see what they were. No, it's part of an old measurement system that isn't used anymore, but ergs for some reason held on. What's more typical for earthquakes would be like megajoules or megawatt hours. Was it megawatt hours? No, electron volts, something like that. Like we use different forms of energy now, but for some reason, ergs is what holds on for earthquakes. I'm not sure why, but there it is. You guys sure are chatty this morning. Making me feel like I have to yell over people just so you can hear me. pH. The pH scale ranges from 0 to 14. A pH of 7 is neutral. Anything greater than 7 is a basic. Anything less than 7 is acidic. Apple juice has a pH of 3.49, so it's an acid. And whole fat cream has a pH of 6.62, so it's also an acid. But it says, what are their hydrogen ion concentrations? For that, we're going to need to come back to the pH formula. And H plus is your hydrogen ion concentrations. So pH equals negative log of H plus. I already told you don't have to know these formulas. Where H plus is just your hydrogen ions. Oops, sorry, you couldn't see what I was writing. No, you don't have to have the formula memorized. It'll always be supplied. So for apple juice, we just set its pH of 3.49 equal to this formula. You're going to need to divide by negative 1. And then because it's the common log, just like the ergs thing we just did, you're going to need to use base 10 to get H plus by itself. I think it's a chemistry thing because brackets and parentheses behave the same. I think brackets is a chemistry notation. Honestly, I don't know. As far as the mathematics is concerned, it does the exact same thing. So let's see. We throw a base 10 underneath each one of these bad boys. That will isolate H plus. And I feel like you're better off just writing it as 10 to the negative 3.49. I mean, if you wanted to see what that is, you know, you're going to get something back in scientific notation. You know what? Maybe we should do that because isn't that how chemistry is often done? Chemistry is done in scientific notation, right? And I believe this is I think this is moles per milliliter or something like that. Yeah, it's in moles per milliliter. And since moles are always done in scientific notation, I say we go ahead and use the scientific notation answer. Boo, he says, but is he asking me again if we have to know this formula? What in the world? This is what happens when people talk constantly when the teacher's educating. This is moles per milliliter. Moles per ml. And whole fat cream. I don't really have a whole lot of space here, do I? Well, tell you what, we'll just have it creep down the right side. We have space on the right side. But it's the exact same setup. The number equal to negative log of h plus. Divide both sides by -1. And then use base 10 on both sides. That's going to isolate h plus. And whatever 10 to the -6.62 is. And of course, it'll be in scientific notation. And if you round it to 3 decimals, you get 2.399 times 10 to the -7 moles per milliliter. I think the L in liter is supposed to be capitalized, isn't it? Like that? I think it's supposed to be capitalized. So it's just a calculator question. Don't really have to think too hard about it. So for part B, we're just supposed to fill out the table and see, and then identify if it's an acid or a base. And basically that's, you see how I did there? Basically. What that means is the number going to be bigger than 6, excuse me, bigger than 7 or less than 7. And you know what? I don't feel like typing all these in. Oh, I don't really have a choice, do I? All right. Well, poo. Negative log of 4.45 times 10 to the -8. I'm just typing it directly into the calculator, into the formula that you don't have to memorize. Equals 7.351. Since it's above 7, that's a base. 2? Yes, sorry. 7.352. Yep. And that is a base. Negative log. It stinks having to type all these in. .444. That is an acid. I bet you this one's a base. Do you know why I know this is a base? Because it's to the -8 and the coefficient on front is larger, which means I'm going to get a bigger number than 7.352. Oh. Yeah, I was going to say it's less. It's less. -8 at the top, it's a larger number. I'll be okay. Yes. But the point is, we still got a number that was over 7. Not a lot over 7, but still over 7. It is still a base. I'm having a small brain fart. Isn't this number bigger than this number?
Yeah, but it's to the negative power.
Oh, to the negative power. You mean up here with the negative sign on the logarithm? Yeah. Yeah, so it's a larger number. And the log of it would be larger, but because it's negative, I'm going further left. So it is a smaller number. Man, that is definitely a brain pretzel. Negative log of 1.8 times 10 to the -3. Uh-oh, what'd I do wrong? Oops. There we go. Very acidic. Yes. No clue. Nope. AP exam is sometime at the end of the school year. Yeah, I mean, I could know, I just don't. I don't know. Sound intensity levels. He says if I wanted to, I would. I guess that tells you something, doesn't it? Sound intensity levels. Logarithms are used to model sound levels. The sound intensity is a measure of the energy carried by a sound wave. This loudness, capital L, is measured in decibels and uses this formula. Did you guys know that a decibel is actually a unit of pressure? So it's the... Oh, I've told you that before? Okay, well then maybe that's why you know it. But yeah, so loudness. And I will tell you this, I don't know why this I sub 0 is in the formula, because we have a number that we use for I sub 0, where I sub 0 is the lowest intensity sound that the average human can hear, which would be 10 to the negative 12. So I, the only thing we don't know in this formula is the intensity of the sound in watts per square meter. Okay. So it says, what is the decibel level of a normal conversation, which right now I'm speaking louder than a normal conversation to make sure that everybody can hear me, because there's other chit-chatting and also people don't listen all the time. But anyway, what is the decibel level? We grab handy-dandy pen and we say the loudness in decibels is 10 times the log of 10 to the negative 6 over this I sub 0 is going to be 10 to the negative 12. No, you don't have to have the formula memorized. We actually don't need a calculator to do this because everything is in base 10. When you divide two numbers with the same base, what do you do with their exponents? Subtract. But what is negative 6 minus negative 12? It's positive 6. So this gives me 10 log of 10 to the 6. And log of 10 cancels and you get 10 times 6, which is 60 decibels. 60 decibels. Normal conversation. I'm sorry? Yeah, it's right there. I didn't make it up. Yeah, so a decibel is, yeah, just like there's a milliliter, which is why we're capitalizing that second letter. And if I had to guess on what a bell is, it might have something to do, it might have been named by, you guys know those like old school diving bells? It might come from that name if I had to guess. No, a decibel. But deci is like 1/10 of a bell. Okay. Anyway, the human threshold for pain is 120 decibels. A jet engine is 150 decibels. How many times as intense is the noise of a jet engine as the noise that causes pain? What'd you say? So here's what we want to do. We know that this is 10 to the negative 12. But you know, I don't know if you guys caught this, we could actually expand this if we wanted to. We could say that this is, and by the way, we're just going to say this is 10 to the negative 12. We could say this is 10 times log of the intensity minus log of 10 to the negative 12. But log of 10 cancels, so this says minus negative 12. So that's plus 12. So what we actually have here is a formula for loudness that no, you don't need to memorize. What just happened to my brain? I missed a parenthesis. It's in the wrong spot. There. So we have a formula for loudness. So we want to know how many times louder it is. All right. Well, we can just drop in the 120 and the 150 into this formula. Let's see. 120 is 10 log I plus 12. Divide both sides by 10. Oh, look. If you subtract 12 from both sides, we get that log of I equals 0. So then what is the intensity? How do we cancel the logarithm? Base 10. Yeah, this logarithm, when it cancels, leaves me with an intensity of 1. So basically, if you go over 1, if you go over an intensity of 1, pain. That's what that tells us. An intensity between 0 and 1, not pain. And by the way, pain, I think, is also where it starts to cause hearing damage. What does pain feel like? You've never felt pain in your ears? You have. You probably just ignored it and thought, I like really loud music. Okay. The other one, let's do it. You guys see what's happening here? If I set it equal to 150, I'm still going to divide by 10, so I'm going to get 15 equals. So I'll just jump right to that to save myself some space. Subtract the 12, and you get that the log of the intensity is 3. So when you isolate the intensity by, again, using exponential base 10, what you get is that it is 10 to the 3 megawatts per, watts per square meter. So how many times more intense is it? It's 10 to the third. It's 1,000 times more powerful. I mean, if you didn't know, you know, you're just supposed to do 10 to the third over 1, which is 10 to the third, or 1,000 times more powerful. More intense, let's say. So jet engine, stand behind it. Yep. It'd blow your ears up. Might actually rupture your eardrums. But it would definitely cause hearing damage. No. And that's why, it depends on how close you are. And that's why if you ever look out on the tarmacs, everybody's wearing those massive ear protection. And some of those, like, I don't know what the airliners use, but a lot of your ear protection can really only reduce like 22 to 26 decibels. So to go from 150 and subtract 100, and you subtract 22 to 26, you're still above pain threshold. So those people are probably wearing double ear protection, if I had to guess. Yes? This guy, he just doesn't want us to finish the notes. No clue. No idea. An archaeologist carbon dates a fossilized bone that is thought to be around 4,500 years old. The archaeologist determines that the sample contains 60% of the original amount of carbon-14. The half-life of carbon-14 is 5,730 years. We want to know, is this a good estimate of its age? In order to do this, you are going to need to be able to write a half-life formula, and you are responsible for knowing how to write a half-life formula because it is an exponential function. Half-life means literally you're multiplying by 1/2. So the formula for half-life, and yes, you do need to know how to do this, is and then it's time in years divided by the length of the half-life. The length of our half-life is 5730. So the only thing that changes for the half-life formula is the length of the half-life. This is always the setup because it's literally half. Okay, so we need to get an estimate for the age, and what we know is that we have 60% remaining. That's what we know. That means if we divide by p, we get 0.6. That's what we're being told. I have 60% remaining. So 0.6 equals 1/2 raised to this fraction. Now I'm trying to type this on a calculator. I'm going to need to type this on a calculator. And everybody in the room, I hope, has access to a graphing calculator. And hopefully that graphing calculator is new enough to have the log base command. Does everybody have log base command? Okay. Okay. Cool beans. Then what we're going to do is we're going to use log base 1/2 of both sides. And if you don't feel, remember from what we were talking about yesterday, This is equivalent to negative log base 2 of 0.6. Just throwing it out there. Just bringing back what we talked about yesterday. So you're going to multiply both sides by 5730. And we're going to see the age. 5730 math log base of 1/2 of 0.6. Let's get the age. 422.813 years. So is that a good estimate? I'd say it is. That's pretty close to 4,500. I'd say it's a good estimate. Only being off by a couple hundred years, that's pretty good. I mean, carbon dating is not perfect. You know, the numbers can be messed with a little bit. Fire will make things seem older than they are. Lightning will make things seem older than they are. Things like that. So it's not perfect. Can we move on? All right. Newton's law of cooling. Yeah, I don't have Newton's law of cooling memorized. You don't need to have it memorized. Time to go back to the front and grab it. We're going to copy paste this to the back. I'm trying to memorize it. TM, T0, TM. Okay. I've already forgotten it. Here, one of you read it to me. Okay, TM. So hold on. What's the variable expression at the front? T of T? Okay, TM. Parentheses. T0 minus TM. And then it's e to the negative KT. Thank you. Okay, there we go. So what do these things stand for? Little t is time. Okay. Every capital T is a temperature. This is the temperature of the surrounding medium. That means the water that something is in or the air that something is in, something like that. It's temperature of the medium. So whatever it's in. T sub 0 is original temperature. And K is going to be our cooling or actually heating factor, because this Newton's law of cooling can also be used as Newton's law of heating. So like if you put something in an oven, it'll still work. The formula still works. A batch of brownies are taken out of a 375 degrees, well, this is clearly imperial, Fahrenheit oven. So that would have been the TM. It would have been the TM. Cools to 150 degrees after 20 minutes in a room at 70. Okay, so since it's in a room at 70 degrees, that is TM. Use Newton's law of cooling to determine how long it will take the brownies to cool to 90 degrees. So because we're saying that we took these things out of a 375 degree oven, what we're going to have to do is assume that that was the temperature of the brownies. So we're just going to assume it's been in there long enough to come up to the same temperature as the surrounding medium. And the only thing we don't know is K, which is going to be our cooling factor. And maybe we were given one that, because I didn't read this. No, we were not given a cooling factor. Interesting. Well, I don't know if we have enough information to find it, to be honest with you. I don't know if we do. I don't know. Well, anyway, let's fill out what we know. The temperature that we're shooting for here is the 90 degrees. So we're looking for 90 degrees Fahrenheit. The surrounding medium is the temperature of the air around. And it says the air around is 70 degrees. The original temperature is going to have to be 375. Oh, there it is. That's why, look, we have to solve for T, or solve for K. There it is. Because we know that we dropped down to 150 after 20 minutes. I've already started writing in blue the second part. So we're going to go ahead and put a pause on this. We're going to put a pause on that. And on the right side, we're going to solve for k. And then once we know k, we'll come back here and we'll fill it out. Cool? Okay. Alrighty. We know that after 20 minutes, we got down to 150 degrees. So 150 degrees, the surrounding medium was still 70 degrees. Our original temperature would have been the 375 minus the air. E to the negative and time is 20. We don't know k. So we're going to use that to solve for k. Then we'll come back and we'll use it to figure out how much time it's going to take to get down to 90.
Wait, why is it negative?
Just because it's part of the formula. There's a negative sign in the formula because it's cooling, which is a decay. So it's continuous decay, which is why it has a negative exponent. Okay? All right. Let's see. 150, 70, 375 minus 70 is 305. E to the negative 20k. Now, when I teach this in Algebra 2 Honors and Algebra 2 and any other time I've ever had to teach it, I have to remind my students, you cannot add these two numbers right here. You can't add them because this is being multiplied to an expression that you can't evaluate. So you're trying to isolate k, you have to subtract 70. Do not add here. Subtract 70 from both sides. I'm going to stop writing the degrees because who cares? Divide by 305. Time to cancel E. How? ln. Use the natural log of both sides. And then divide both sides by negative 20. So our k, what? Our k is the natural log of this fraction, whatever that equals, and we will then divide that number by negative 20. And we'll take this out to 3 decimals. Let's see. Yes? Of? Yeah, of course. It doesn't matter if you could put it on the top if you wanted to. It won't make a difference. But I'm going to type it on a calculator, so I'm not even going to worry about where it goes. I'm going to say, all right, calculator, what does k equal to 3 decimals? I don't like that it's got a 0 after the 0.0. So let's take it out to 4 decimals, 0.0669. Okay? I'm going to say 0.0669. It's always a guy. It's always a guy. There. Now we can figure out this T. Go back to blue. Original temperature is the 150 degrees. So now we're trying to cool from 150 down to 90. So we've got the 150. The surrounding medium still 70 because we're trying to cool down from 150 degrees to 90. If you wanted to, you could have said that this was 375. It won't make a difference. Except for, in the end, when I solve for T here, this T will be how long it took to cool from 150 to 90. If you put 375 here, it's how long total it took to cool from 375 to 90. So as long as you remember, when it says how long will it take, that means I'm going to have to add 20 to my answer. Because mine is how much longer does it take. Does that make sense? I'll tell you what, let me get it done and then I'll explain. I'll write the answer in 2 formats. Total time and more time. Okay? Anyway, we've got this negative 0.0669 T. That's 80. Subtract 70. Divide by 80. Let's just pretend that we don't know that that's 1/4 because it's not worth reducing or anything because you're going to grab a calculator anyway. So I'm going to do the same thing I did here. Take the natural log and divide by this number. Natural log of this. Again, we're pretending that we don't know that that's 0.25 in there. I already explained that, but yes. Okay, but don't worry, I'll say it again in a minute. Divide both sides by that number. So my answer, because I said the starting temperature was 150, my answer is going to be the amount of time, the amount of more time it takes to get down to the 90 degrees. The total time will be my answer plus 20. So it's all about the way the question's worded. And you know what else? Because we have a graphing calculator, I'm just going to do negative second answer. There. So it didn't round it at all. It took an exact answer for me. 20.717 more minutes. Or 40.717 total minutes. It's all about the way the question's worded. I would argue that this one wants the total time, but I wanted to do it this way. That way you don't get tripped up in words on an assessment if it says how much more time. So this is the difference. This is 20 more minutes for a total of 40 minutes. Yes, dang. That's because you used a rounded number here. I didn't use the rounded number. I told the calculator to use the exact number. But if you rounded to 3 decimals, your answer's still correct. Don't worry about it. Okay? I just didn't want to because I had the ability to get an exact answer. And you know what? I didn't know it. But that calls it for today, nerds. Thank you.